Good afternoon. So as I mentioned last time, I want to go over one convergence property for the Fourier series. And I'm not going to prove it, and there are different theorems about convergence, but I will just talk about one of them, which is useful to know, and it covers pretty much all the functions we're going to deal with in this class. This is one of those topics in which there doesn't seem to be an easy and short way to state these properties, these theorems. So I'm going to just illustrate it with examples and various graphs. So for a moment, for a while, take a moment to write down. You may pause the video at some point and write down what I just wrote here. We're going to need some notations for this theorem. Some of you might remember this from Calculus 1. So if you look at the sided limits, fa plus, this is a notation for the right limit. So as x approaches from the right, so if you take a limit, let's say at the point A, and you approach A from the right hand side, then you denote that by A plus, right, in the limit sign. And if you approach it from the left side, you denote that by A minus, the limit from the left. So f of A plus, f of A minus are notations for the right and left limits at a point, left and right limits at a point for a function. And there's a similar notion for sided derivatives. So a function, maybe if it's differentiable at a point, then of course there's no distinction between the two, right? So if the limit exists at a point, or if the derivative exists at a point, there's no distinction between left and right. But a point may fail to be, a function may fail to be differentiable, but the left and right derivatives may still exist. So remember the definition of the derivative with the difference quotient. In a similar manner, you can talk about the right derivative or the left derivative, f prime of A minus. So what about the convergence? So suppose you have a function with the properties we know already that we used in order to compute those Fourier series. So let's say the function is piecewise continuous on a symmetric interval minus c and c, and periodic with period 2c. Now remember, you can also obtain that periodic function by extending the original function. So you can start with a function between minus c and c, and then you can take the periodic extension, because the Fourier series will cover the periodic extension as well. So although the original function is between minus c and c, remember the Fourier series represents not only the function, but its periodic extension as well. And suppose there is a point at which the one-sided derivatives exist. So see, that's an additional condition for the convergence. That's the difference between what we had before. Now we also require that the one-sided derivatives exist. And in that case, the Fourier series will converge to the mean value of the sided limits. Most of the time, this mean value is just f of x. Because let's actually illustrate quickly here. If I have a function that looks like this, let's say, a piecewise defined function. And let's say this point here is 1, and the y-coordinate to the left is 3, and the lower one is 2. Well, that doesn't make much sense. Let's say 2 and 5. No, not 2 and 5. Let's say this is 2 and this is 1. Just to make it more realistic in terms of the distances between the points and the origin. So, for example, if I look at 1, right, if I look at x equals 1, there's no distinction between f of 1 plus, f of 1 minus, and f of 1, because f is continuous at 1. And by the same token, there's no distinction between f prime of 1 plus, f prime of 1 minus, the derivatives to the left and to the right, because the function clearly, if you look at the graph, is differentiable at 1, at x equals 1. So the whole distinction here with the left and right limits is for the points in which the function may fail to be continuous. Now remember, it's piecewise continuous, so the sided limits still exist. So at 2, if I look at x equals 2, the Fourier series for this function will converge to the left, to the semi-sum, right, to the average between, or the mean value between the right limit at 2 and the left limit at 2. Now, as x approaches 2 from the right, the limit is 1. As x approaches 2 from the left, the limit is 5. So then the series will converge to the average value of these two-sided limits. So that is the main thing to keep in mind in terms of the convergence. So these Fourier series, in other words, and let's actually write it as a remark before we worry about subtleties like this. For all practical purposes, in most cases, the Fourier series will converge to the value of the function f of x as expected, right? Because remember, you're trying to represent the function by its Fourier series, except at points of discontinuity, in which case it approaches the average value of the sided limits as the theorem stated. And if the point itself doesn't have finite derivatives, sided derivatives, then the convergence is not guaranteed by these theorems. So basically, we're not going to deal in this class with functions that may be piecewise continuous but are not differentiable. I mean, this is piecewise differentiable basically. So here's an example. You could have, for instance, f of x square root of x. Let's look at square root of x over the interval 0, 1. Now, if you write the Fourier series, the convergence at 0 is not guaranteed, because the sided derivatives, so for example, if I look at f prime of 0 plus, does not exist. I don't have to look at by definition. Remember, f prime of x is equal to 1 over 2 square root of x. Clearly, this doesn't exist at x equals 0, right? So the derivative doesn't exist at that point. So these are the situations in which you don't have a guaranteed convergence. Now, the reason so that's as much I want to say about this topic. The reason I want to go over it, in addition to the fact that you should be aware that, as with all series, the convergence is not guaranteed to any point on the function, for the function you represent. There's also a nice opportunity for you to learn some cool identities that relate, for example, pi, or quantities that depend on pi with series. So you could, for example, provide various definition of pi. You can also show your skills to students who didn't learn this before. So you can enter a series and you can say, okay, this is going to be pi or something in terms of pi, because you learn in this class that it converges. I mean, it's a limit. It's the sum of a Fourier series. So on the next page, I'm going to go over a couple of examples like this, and maybe some of them with Maple as well. So stay tuned for the next page. All right, so let's illustrate with a couple of examples, and write down this example, and for the series, take it for granted for now. You're more than welcome to compute the series yourself to convince yourself that this is correct. But let's focus on how that theorem works. If we plug in a point, an actual value for x into the Fourier series, what does that series converges to? That is the question. So we start with a function between 0 and pi. Let's say it's equal to 1 between 0 pi over 2 and then 0 from pi over 2 and x. I should have actually wrote here on the left, this can be extended, remember, because I'm going to talk about a cosines, to be more precise, a cosine Fourier series, which, remember, it can be extended to an even periodic extension. So the actual Fourier series, in this case, the Fourier cosine series, is given by this. So as I said before, again, if you want, you can check yourself with the definition if you want, or with formulas. So that theorem, remember, covers the full real axis, right? I mean, because a Fourier cosine series can be extended to an even extension to the left. So actually, if I were to, let's do it here quickly. If I were to sketch this, right? So that's the seed, so to speak, between 0 and pi. Then it can be extended to an even extension. So you flip it over the y-axis. So this will be minus pi. And then, of course, you can repeat the pattern left and right. And the Fourier theorem, I mean the convergence theorem I mentioned before, will cover the full periodic extension. All right, so if you plug in a point for which the function is continuous, for example, if I plug in 0 for x, the periodic extension is continuous. So if x is 0, then the Fourier series will converge to f of 0, which in this case is going to be equal to 1. By f of 0, by the way, I mean the full periodic extension. I should probably use a different notation here because little f of x denotes the original, but the extension is over the whole axis here if you look at the graph. So it's guaranteed, and we can check with the Maple or with computer algebra system that if I replace x with 1 into the series, x with 0, I'm sorry. That's going to be equal to f of 0, which is 1 from the graph. So this provides basically a way to write, for instance, a different way, I mean, another definition of pi, for instance, if you want. Because if I move 1 over 2 to the right, then, and by the way, cosine of 0 is 1, obviously. 1 minus 1/2, so and then multiply by pi over 2. So if I start with the right hand side, that's going to be pi over 4 equals summation of from 1 to infinity 1 over n sine of n pi over 2. So you have these cool interesting convergences, I mean, or definitions of pi, so you can maybe even show off your skills to those who didn't know where they come from. You know, like replacing pi with a series, and you can prove that that's correct if you check with Maple. Maple or similar programs should be able to recognize when these series converge and to what value. All right, so this point 0 is a point of continuity, but let's say you plug in pi over 2 in this series. So let's say you do x equals pi over 2. Because the point is discontinuous, I mean, at this point the function is discontinuous, the function will not converge to f of pi over 2, but it will converge to the semi-sum of the sided limits at pi over 2. So that means, let's see, the sided limits, the limit to the right at pi over 2 will be 0. So if x approaches pi over 2 from the right, it's 0. If it approaches pi over 2 from the left, it's going to be 1. So it's going to be 1 over 2. And that's going to be equal to 1 over 2, let's see, 0 plus 1 over 2, right, 1 over 2 plus 2 over pi, the summation from 1 to infinity, 1 over n sine of n pi over 2, and cosine of n pi over 2, right? Because you replace x with pi over 2. And actually, in this case, you can check without the calculator that this is correct. Because see, 1 over 2 cancels. So that implies that this series should be 0. So 2 over pi summation from 1 to infinity, 1 over n sine of n pi over 2, cosine of n pi over 2. And as it turns out, this is actually kind of a trivial example because there is a formula. If I bring this 2 inside, there is a double angle formula which states that 2 sine x cosine x is sine of 2x. So as a matter of fact, this series is 2 sine of n pi over 2 cosine of n pi over 2, which becomes 1 over n sine of 2 n pi over 2, which is just n pi. Now sine of a multiple of n pi is 0, or if you look at the unit circle, multiples of 2 pi sine of multiples of pi is 0. So that means this is equal to 0. So I basically showed you that this is indeed correct, that the theorem does indeed says, I mean, it is correct. I mean, in the sense that this is an example you could check yourself without the computer. So we're going to go over a couple of more examples before we call it a day. And I'm going to show you those examples with Maple as well. So stay tuned for the last page. All right, so here's another example. We actually met this example before. Again, take for granted the Fourier series provided here. So in the previous example, we dealt with the Fourier cosine series. This time, we deal with a Fourier series in general. So the original function is now defined from minus pi to pi, and it's neither even nor odd. It's 0 between minus pi and 0, and x between 0 and pi. And then we extend it to a periodic function over 2 pi. So the Fourier series will just represent the entire periodic extension, and it will converge, according to the theorem, to every point of continuity. And if it's not continuous, it will converge to the average of the sided limits. So once again, if you plug in a point in which the function is continuous, you're guaranteed to be to converge to the value of that function. For example, what happens if I plug in x equals 0? Well, x equals 0 is a point of it's a point of continuity, so it's continuous at that point. So the Fourier series will converge to f of 0. So basically f of 0, which is equal to 0, is guaranteed to be equal to pi over 4 minus 2 over pi, summation from 1 to infinity. Cosine of 0 is 1. So that's going to be 1 over 2n minus 1 squared. Sine of 0 is 0 in that case. So that's it. And this gives you yet another identity, right? I mean, it gives you another identity in terms of a sum of the series. So for example, if I move minus pi over 4 on the left, 1 over 2n minus 1 squared, and then multiply both sides by minus pi over 2, you get pi squared over 8 equals summation from 1 to infinity, 1 over 2n minus 1 squared. If you write this series by term, that's going to be 1 minus 1 over 3. It goes to the odd numbers only, plus 1 over 5, minus 1 over 7, plus 1 over 9, and dot, dot, dot. And again, you can play with Maple or similar and plug it in and see if you get the correct answer. So there's another way of actually obtaining this. Let's see, if I plug in pi, actually this is going to end up with pi squared over 8 as well, but let's check. What happens if I plug in pi over, x equals pi? Let's pay attention to the graph here. Pi is a point of discontinuity. The series will converge to the average value of the sided limits at pi. Right limit is 0, left limit is pi, as x approaches pi. So pi over 2 should be equal to, now I plug in pi everywhere, pi over 4 minus 2 over pi, summation from 1 to infinity, cosine of 2n minus 1 pi over 2n minus 1 squared, plus summation from 1 to infinity, minus 1 to the n plus 1 over n sine of n pi. Now, sine of n pi is again 0, and cosine of 2n minus 1 pi, now we met this before, remember cosine of n pi is minus 1 to the n. It cycles through between minus 1 and 1 depending on whether n is even or odd. So pi over 2 over here should be equal to pi over 4 minus 2 over pi, the summation from 1 to infinity. Now this is going to be minus 1 to the 2n minus 1, which is minus 1 because it's an odd number. And actually we obtained the same series as before. We pretty much confirm basically what we had before. So let's see, minus goes outside the series. And that's just another way of obtaining the same series as it happened, right? So let's see if I move, it should be pi squared over 8 when everything is said and done, right? Because it's the same series. So if I move pi over 4 to the left, that's pi over 2 minus pi over 4. Let's see, this it's pi over 4. And then multiply both sides by pi over 2, and as expected, we get yet another way of proving that this series is pi squared over 8. And there are some homework questions like that in which you're asked to prove or show some of these identities by using a Fourier series and by plugging in an appropriate value. To summarize, again, in most of these cases, in all of these cases in the homework, the series will converge to the value of the function or to the average value of the sided limits if the point you plug in happens to be a discontinuity. So that's it for today. We'll see you next time.